Oh, look at this. They put spare batteries in here. That is good to know. All right, are you raising your hand? Oh, okay. Who'd like to start us off with a prayer? Anyone? Anyone? Oh, could we have someone new? I sure appreciate it. But would anyone like to do it? Go ahead.
Excited about learning and keep moving forward. And we ask for blessing on those with COVID right now that they can heal and recover, and that we can go back to somewhat normal. And we love you so much. We say these things in Christ's name.
Amen. Thank you. Thanks for praying that I'd have the Spirit with me. Yesterday was not a good day, and as I thought about it this morning, I think I lost the Spirit for most of yesterday. Started off well, but then something happened, and it was just a miserable day. And I'm doing a lot better today, thank goodness. But yeah, it was just horrible. I'm trying to think of the quote. Well, I'll look it up and I'll share a quote with you, give you more insight. So here's. There, is that better? So here's a few warm-up problems. The first one is a warm-up problem. So what I'm going to try to do is, I started to put warm-up problems up there. The first one would be something that I would hope you'd be able to do from the study and homework stuff that you did coming into class. Okay. The second one also might be something. The later one is something to stretch you. Okay, for those of you that, yeah, we're doing a linear transformation on you. I'm going to stretch you. I'm just kidding. All right, so it's something to really get you to think. Okay. So when I did the flipped class in 113, some of you were in that class. When I surveyed the students, a third of the students said the preparatory material was just right. And so they'd come into class ready and they'd continue to learn. A third said the preparatory material for before wasn't enough and they were lost in class. And a third said, I don't know why I need to come to class. I learned everything that I need to come in. I already learned everything that before I came to class, so why do I even come? So my strategy was to start off with easy, medium, and hard level problems in here so that there was kind of something for everyone to start with. So I'm trying to do that same strategy. I'm going to switch slides in just a second, but we will come back to this. We didn't talk. I have a few slides to talk about where you use a basis. The 2 o'clock class, I got to talk about that, but I didn't get to here. And they're related to things that we've talked about, I've mentioned before. So I have 3 examples. So digital imaging in screens. You only need 6 numbers. So it's basically a 6-dimensional field, 6-dimensional space. The colors you see on the screen are. And the color, it's your red, green, and blue, and the hue, the saturation, and the luminescence. So you give those 6 numbers. Those are the you can kind of think about them as the coordinates. Actually, is what we're going to talk about today. But those are the building blocks of the colors that you see on the screen. Red. If you don't want to think about hue, saturation, luminescence, just think about the red, green, and blue, because those are 3 colors. You can create all of the other colors with mixtures of those, and there's no redundancy there. They span all the colors that they can make on the screen, and there's no redundancy. So if you give someone a color, then there's exactly one combination of the red, green, and blue that will get you there. So that's one example. You could pick another one. So red, green, and blue is not what you learned in primary as the primary colors, right? You learned yellow, blue, and red, but it's really yellow, cyan, and magenta. It's these cuts right here. Those are really the primary colors. You could use those as the basis. But they use red, green, and blue because those are what your eye picks up, are the red, green, and blues, and then your brain combines those. So they actually make the pixels in terms of red, green, and blue. So the digital image compression, remember this one. You can take any, this is for black and whites, but you can take any 8x8 set of pixels, and you can write them. You could create a basis where you just highlighted one of the pixels, and you could have 64 of those, each representing the different pixel. This is a different basis. Either one of them, you could make each picture, each 64, each 8x8 array, you could make it exactly, either one. The advantage with this one is that you rarely need to use these ones on the bottom right corner. And so, and even if you leave them out, it doesn't change, it doesn't change very much what you see. So it allows you to compress things. Whereas if you just went with one cell each, then if you leave one out, you have a hole. And it's easy to see that hole. So, yes? Oops. You need an all black one as well? So the first one up there is like the average one. So that white one, so when you change you can change the, change the level. So that's the one that you could make it all black and you'd be good. Okay, and then for sounds, sound storage and compression, sine waves. And you don't just need all sine waves, you actually only need some sine waves. They'll do sine of x, sine of 2x, sine of 3x, sine of 4x. So you actually don't need sine of ax, where a can take anything. There's actually just separate ones. They use those because sine of x and sine of 2x and sine of 3x and sine of 4x, they are actually orthogonal so to each other. It's weird to say that they're perpendicular. That's one reason why we have a new word, but we can explain later. Hopefully we'll have a time to talk about why they are orthogonal to each other. But so those are some examples of bases that you may not have thought of. Why deal with coordinates? Here's 3 examples, because I remember in this class thinking, why do you want to change coordinates? We've got the standard basis, x, y, and z. Why would anyone want to change coordinates? So here's a few examples of why you might want to change coordinates. One, there are times you can see the planes flying around the Earth. If you're trying to give directions or make sense of things from the way you face, like if I'm in the plane, it's easy to give directions about which way the plane is facing now, what's up and what's down relative to the plane. But if you're down on Earth, the plane could be going in all sorts of different directions, and it's easier for you to think something that, your up is different, maybe different than the up in the plane, right? And you might do north, south, east, and west stuff, where they're doing right, left, and up and down. And so if you're trying to get to the same spot, or trying to think about maneuvering the plane, then you could think about different coordinates based on those different directions. So does that make sense? Sort of. Like if I face like this, okay, it's easy for me to talk about, I'm going to go this way and this way, right? But Grant over there, he's facing that way, and it's easy for him to talk about going this way and this way. And so we could still get to the same point, and I would say, well, I'm going to go 5 feet this way and then 2 feet this way. You might have to say, I'm going to go 7 feet this way and a negative 2 feet that way. So, what's a negative 2 feet that way? Is 2 feet. So, if some of you are a little geeky like me, so I sent out that video about the collisions. Well, there's a follow-up video where he gives an explanation, a second explanation, and it has to do with light waves. And at first, he uses these light waves, and they're kind of crazy, but then he changes, he basically changes the coordinates, changes the basis for what they're working on, and then the light waves turn out to be really nice and have this really nice property, and makes it easy to do some calculations, and he can do some reflections. So sometimes just things work out nicer if you change the base mathematically. And last, here's an example of changing a base. I have a scatter plot down there. So if you think, you could think about this like, we'll just think about it as height on the x-axis and weight on the y-axis. And that's about maybe what you'd get if we had a bunch of people, like males or females, heights and weights. And we can think about heights and weights, that's easy for us. But there's also another natural basis here. You can think about that long line right through the middle. We have this kind of ellipse, and it looks like this direction is really important, and this direction is really important. And this direction you might call size. Because the further you are over here, you're taller and you weigh more. Down here, you're shorter and you weigh less. This dimension is shape. The more you are up here, you're shorter, but you weigh more. Right? So this is rounder. And down here, you're taller, but you weigh less. So this is tall and skinny. You know, this is stretched out. This is smashed down, something like that. So statisticians use this all the time, where they do data reduction, and then they'll just take the first what are called principal components. So, which is basically a change of basis. Yep.
So if I am changing the basis on this scatter plot, it would make it so it's, I'd like basically be shifting it.
Yeah. So yeah, you basically have a rotation, right? And so you can think about size and shape instead of thinking about height and weight. But we'll do more with principal components in the next chapter. So these are just some examples of like why change coordinates. Okay, so go ahead, you can keep working on these, and I'm going to get up the next problem. Okay, let me have your attention. So here's our favorite matrix: peanut butter, bread, fat, protein. Okay. I'm sorry if any of you are allergic to peanut butter. So, I could give you like maybe a daily goal that I want, and I could tell it to you in terms of peanut butter and bread. In this case, 2-2. My goal is 2-2. And if I tell you that's peanut butter bread basis, this is a basis for the fat and protein space. Okay, these are linearly independent. I span the whole fat and protein space. They're linearly independent, so this forms a basis. And so I can think of my coordinates as just as weights of each of these columns, or I can think about it in fat and protein. Either way. The fat and protein in this case, that's like the standard, that'd be the standard basis. But if I say, let's convert. So if I said, hey, my goal is 2-2 in peanut butter and bread, what's my goal in terms of fat and protein? How would I get my goal in terms of fat and protein? So we can do matrix multiplication. Let me do the in-between step. If these columns are a basis, then this means when I say 2, 2, that means I have 2 of the first column and 2 of the second column. So I'm doing this. Which is just matrix multiplication, where I can just do 2, 2, and then actually, my board work is awful. Okay, you get 3322. So I could think about this as peanut butter and bread. I could think about this as fat and protein. They give me the same information, right? As long as I know the basis you're talking about, they give me the same information. So, okay. So we can go back and forth. The question is, like the harder questions are like the ones that are number 1 on the slide. So, it's like knowing 3322 and then finding the coordinates here. So if I said, what are the coordinates in the peanut butter and bread basis to get me 3322 in the standard basis, or the fat and protein? Because this is the standard basis in this case, because this is 33 fat and 22 protein. So it's just telling you what it is. So how would you solve this problem? Sorry, what was that, Sophie? Do the transpose. I think you're thinking inverse. Yeah, if we knew an inverse, so this is one way. So we could use the formula we know for a 2 by 2 inverse, multiply it by that, and it would tell us that. Great. So there's one way. What else? Yeah, Braden? Put it into an augmented matrix and row reduce. So we could do 15, 8, 1.5, 3, 33, 22. And this would help me know what my xy is, how many of these and how many of these. That would be my solution. So to find the coordinates. So now we can row reduce. So that would be the strategy for doing number 1 there. Michelle and I are both trying to control the mouse. So, okay. So the way we would set up 1 and work on 1 is we could do row reduction. We can't use Sophie's strategy here. Why not? It's not a square matrix. It's not invertible. But we can still do this one. We can 1, a minus 1, 2. So this is the coordinate in the elementary basis and the standard basis. Okay, this is 1x minus 1y, 2z. Okay, just thinking as our regular x, y's, and z's. But here I can think about this as B1 and B2. I need to figure out how many B1s and how many B2s do I need to get this. And then that number of B1s and that number of B2s are my coordinates. Okay, so I can row reduce. I'll take a minus 1 of this first row, add it to the second row. So that'll make this a 0. That'll keep that 1. And a minus 1 here. What do I get? A minus 2. Okay. And then here I have 1, a minus 2. Here I have 1, 2. I can subtract this row. And did I make a mistake? Did I put 2 on the bottom?
No.
Oh, is this impossible? So, so a minus 1 here, a minus this row, add to this row. This will be 0. This will be 4. -4? Just 4. +4, yeah. So it should have been a -2, apparently. I didn't get that in there. All right, so there is no coordinates here. This does not live in the span of these two vectors. So we don't have coordinates that we had put in there. I did not mean for that to happen. You want to get on and edit that thing for us? Well, maybe we can do that between classes. So, but remind me. Okay. It was supposed to be 1 and a -2. Right, because then you would get, if this was a -2, then this would be 0, and you just end up with 1. So this x is 1, y is a -2. This is 0, 0, 0, 0. So the coordinates would be, B1 would be, I need 1 B1 plus a -2 B2s to equal V. Did I call it V on the slide? So the coordinates of V with the basis B is 1 and a -2. Okay, sorry, that was my mistake. All right, questions about coordinates? Yes? Yeah, so the coordinates with respect to the basis B of V, so the coordinates of V with respect to the basis B are 1 and a -2. What is the basis? It's these columns. This is the one. In the problem, here, can you pull up the thing? So here's, the basis is the columns B right here. So I said B, this is the basis B of some plane. Okay, so these are my two vectors I have to work with. So coordinates in that basis are how many of the first and how many of the second do I need? So I needed 1 of the first, a -2 of the second to equal 1 to -1, a -2. So we'll get that edited out. So here and then there. Oh, right. So yeah, if you're thinking about a plane, yeah, a basis is, these are like our standard two vectors we think of as with the plane, we go 1x and 1y. Okay, but we don't have to work with those. We could also think of, we could work with these two. And if I pick a point here, I can say, oh, that basis is, that coordinate with respect to the standard basis is 3, 3. Okay, 3 of these plus 3 of those. With this one, it looks like it's about, yeah, it's like maybe 3.5 and 2/3. So 3.5 and 2/3. So I could say that's 3, 3 with the standard basis, call it E for elementary. Well, that's the same as 3.5 2/3 with my other basis. If I called this, I'll call it the blue basis for my blue vectors, whatever that's called. So if these are my basis vectors, then I need, oh, I made a mistake. Well, I just needed to specify which one was my first one and which one's my second one. So yeah, this is B1, this is B2. So I have to know which one I'm taking 3.5 times and which one I'm taking 2/3 times. Because if I go 3.5 this way and then 2/3 of that, I'm not going to end up in the same spot. So I do need to know which is my the first one I'm talking about, which is the second one I'm talking about. Yeah, you could do whatever. You can call it whatever you want. Doris. I like Doris. Okay. Other questions about a basis or coordinates for a given basis? Okay. The big reason that we that we work with bases and the non-standard basis is that it turns out that every basis, especially invertible matrices, they have a natural basis, and it's usually not the standard basis. They have a very natural basis that tells you a lot about the transformation in the system that it describes. So, and that's coming up in chapter 4. Okay, let's talk about linear transformations. Okay, so we're starting, so we just finished 3.5. We're moving on to 3.6. Okay, so transformations. And I owe an apology. I wrote up incorrectly the homework last time, and I wrote up an email on Learning Suite, and for some reason it never got out. I thought I hit send, maybe I didn't hit send to clarify the homework. So some of you realized something was wrong because 3.6 isn't due until next Tuesday. So I did try to send out an email and clarify, but something went wrong. I apologize. So the actual homework due for next time is that, and some of you already read 3.6. If you already did, great. You have more time this weekend to go party with a mask on in socially distant settings. So, okay. But I apologize for that. So transformations and context. So transformations are a bit of an abstraction. If you're working in contexts like our peanut butter and protein fat, peanut butter bread, protein fat, then when you do a matrix multiplication, and I take a 2, 2, where this is peanut butter and this is bread servings, then I do a transformation to I end up on a different set of axes. On a protein, well, I think I did fat protein over there. Fat protein, and I did, what do I get, 3322, so something like this. Okay, over 33, up 22, and it doesn't make, I'm like, this 2 has meaning, right? These 2s have meaning. This is 2 servings of peanut butter, 2 servings of bread. I do a matrix multiplication. I transformed what these mean. This is 33 grams of fat, 22 grams of protein. It doesn't really make sense to put that vector on here. Because then you're like 2 breads and 2 peanut butters become 33 breads and 22 peanut butters? I mean, like, I think I reversed that, but yeah. Peanut butters, breads, become 33 peanut butters. Like, that doesn't make sense. But if we get rid of the contexts, and we do think about matrices as just moving vectors in the plane without context to another point in that same plane, then we can start talking about transformations. There are contexts where you stay in the same plane. Here's one that we'll look at next week. This is rabbits. This is foxes. Okay. Rabbits are better. Yep. But my high school mascot was a rabbit, so rabbits rock. Okay. At least we're not like one of the 10 wildcat mascots there are in the state. So, okay. So rabbits and foxes. If I know the population in year 1, you can model it as a linear transformation. Knowing how many rabbits and foxes there are in year 1, you can predict what there will be in year 2. And so it still makes sense to end up on the rabbits and foxes axis. So, so linear transformations, they ignore the units, and they just think about going from 2, 2 to 33, 22, ignoring that this is peanut butter bread, fat protein. Okay, and it's a way to help us get holistically what's happening with the transformation. When we do a matrix transformation, we can sometimes we can easily think about what happens to all the points in the plane at once when we multiply them by a matrix. Yes?
Well, I'm trying to think about, but I'm trying to think about like, why in the world, in this case, it looks like we're just doubling it. But why in the world do we even want to rotate it 9 degrees counterclockwise? What is beneficial for knowing about clocks and rabbits?
Oh, like what's the connection with transformations?
Yeah, why would we rotate it 9 degrees?
So the question isn't about, the question may be less about why would we rotate it. We would have a model that we think fits reality, right, or is pretty close to modeling what happens. And then it might, that whatever that transformation is might help us to figure out what's going on in the system year after year after year after year after year. So, yeah, so don't think about doing the transformations first. Think about understanding the transformations as a way to make sense of a phenomenon. But we're also going to use it just to make sense of matrices and matrix multiplication. Yes? Like, are there infinitely many? If we know that 22 goes to 3322 and that's it, there are lots. Because we just know that A, B, C, D, 22 equals 3322. We won't be able to solve for all of A, B, C, and D here. We'll be able we'll get at least 2 constraints, but we might have two free variables to move around. There's more than one. Another way of saying that in terms of transformations is there's more than one way to transform this linear transformation to put this point to there. So, speaking of linear transformations, okay. The intuitive idea of a linear transformation. This isn't what the book's going to tell you, right? They're going to tell you a transformation takes t of c of x to c of t of x and t of u plus v to t of u plus t of v. They're going to tell you something else, okay? But the idea of a linear transformation is it's any transformation in the plane that takes lines to lines, so lines stay lines, and the origin has to stay fixed. Okay? That's intuitively, those are the transformations we're talking about. Lines can't become curved. You could there's lots of nonlinear transformations. You could take all the lines going this way and end up transforming them so they're all quadratics or something like that. Or you could do this kind of smooshy transformation, but those cannot happen with matrices. So one of the big theorems at this point is all possible linear transformations can be written as a matrix multiplication, and all matrix multiplications result in a linear transformation. They will always take lines to lines, and they will keep the origin here. They'll keep the origin there. You can make this connection back to just scalar multiplication on a number line, okay? If I have a scalar s times a number, if I have s times any number, then no matter what the number is, no matter what s is, the 0 goes to 0, right? The 0 stays fixed. You're just stretching and shrinking. In this case, you can change directions. You can rotate it 180 degrees if s is negative or if n is negative. But the 0 stays here. Similar thing with the matrices. The origin's going to stay when we do this multiplication. So we have a lot more transformations that we can do. It's not, we can stretch and we can shrink. Here we can only rotate 180 degrees. With 2x2 matrices, we can rotate any angle that we want. We can also shear. We can also reflect. And I've got these somewhere. Stop it. I'm just kidding. But I just need to be clear about what we're doing. Okay, so here's shear transformations. Can you guys see that? So shear. So I'm going to take the plane. So here's the plane. I can shear it, so I can take it and go like this. This line stays exactly the same. Anything on this line stays, but it slides this way. So that the x-axis here goes like that. And the line that was here becomes, goes parallel to that. So you go, whoop, okay? Or this way, you can shear it any way. So the shear transfer, most transformations involve a shear. Anytime you're dealing with a 2 by 2 matrix, you can do this in 3 by 3 or 4 by 4 too. But if the absolute value of C does not equal the absolute value of D, of B, I think this is true. Okay? Then there's a shear somehow. So if these aren't the same number in absolute value, if they're the same number of ones, just the negative of the other one, it doesn't have to be a shear. But if these are not equal in absolute value, I think you've got a shear going on there. Can't prove it right now, but that's just my intuition. Scaling, so you can scale things up, scale things back. If you just change the ones in the identity matrix to a different number, it just scales everything. It's the same as multiplying by a scalar. You can reflect things along different lines. You don't have to know this cosine, sine, negative cosine stuff for reflections. But if you were just rotating 90 degrees, we can think it, or 180 degrees, those standard positions we can think about. So that's an example. I'll put this online too, so you guys can have all this. We can project. So when we do a transformation, we might go from 3 dimensions down to 2, or 2 dimensions down to 1, or 5 dimensions down to 1 dimension. So you might end up with a projection onto a line or something onto a plane. Okay. And that happens if you get a row of zeros, or anytime you have linear dependence in your columns, there's going to be some sort of projection. And rotation. So the general rotation for a 2 by 2 is given by this formula over here on the right. Cosines, if you give me an angle, then I can just plug it in to those cosines and sines, and that'll tell me what I need to do to rotate it that far. So, and rotation with the dilation. I don't know if that's important, but, and you can rotate things in space. And in fact, every time you do a row operation, it's just doing a transformation of the plane. When you switch 2 rows, you're actually just rotating the plane or the 3-dimensional space. When you, if you add a multiple of 1 row to another row, you're shearing. And if you multiply 1 row by a non-zero constant, you're just stretching it or shrinking it in a certain dimension. So this is an elementary matrix here. This A is an elementary matrix that would switch some row orders around, and it ends up just being a rotation. If you think of a cube, it just rotate the cube around. Change your x, y, and z coordinates to like z, y, and x or something. Reflections, I don't know if those are that important, but yep. So this is, if you want to study 4-dimensional things, the best way we can make sense of it is to look at shadows of 4-dimensional objects in 3-dimensional space, and this is what you do with that. Yes.
I don't know about in Math 215. I don't know what labs you guys are doing in Math 215, but I know there's a lab that you take like a picture and then you do shear and you rotate and stuff like that through Python. So I don't know if you have done that, but I thought that was a cool lab.
Have any of you done that yet? I doubt it's coming up yet since we're just talking about transformations, but for those of you in 215, that might be coming up. Okay. So those are some kind of general overview things. So you don't need to know a lot of that to sit down and actually figure out which matrices will do which transformations, if the transformations are pretty simple. So here's a few. Why don't you guys try these out? Maybe take 3 or 4 minutes, see if you can come up with these. You're welcome to work with your neighbor. Oops, sorry. So there's two different ways to approach these problems. There's actually three different ways. We'll probably not have time to talk about. Maybe there's four different ways. There's lots of different ways you can approach these problems. So this is the way I was comfortable with when I was in your shoes. I'd write down a general A, B, C, D, and then I'd multiply out and just start solving the equations. So once I get to here, though, if I recognize something, the solution starts to, I can save a lot of work. I don't have to start doing elimination or substitution. What can I use here to make this easy in this particular case? For this side to equal this side, I have to have the same number of x's and the same number of y's here as I do over here. So what does A have to be? A has to be a -1. What does B have to be? 0. Okay. So for these polynomials to be the same, the coefficients all have to all be the same. So that'll save you some work. So I can think about that as plus 0y. I can think about this as y 0x plus a y. So that means A has to equal a -1, B has to equal 0, C has to equal 0, and y equals 1. D equals 1. There. So then the matrix is A, B, C, D. You can get the same thing if you can do substitution and everything, and it should work out. Okay? Yes, in the back. If you got 1 for A and B, and C and D, I think you threw in a rotation then. So that would end up with like a -y and x. So, yeah. So I think, yeah. So it should be exactly this. Okay. Good question. So another way is we could just look at this side and rewrite this in terms of x and y's like I have this. And then think about it as a matrix. What matrix do I have to multiply by to get this side? This is the kind that this is what the book emphasized. They gave you crazier ones like a -x minus y plus a z, and then 2y minus 3z, and 5x plus 2y minus a z, and they give you this, and you're like, what's the transformation? Well, if you're going to do it this way, just look at this side. Let's start looking at each of the columns, and I can think about this as a -1, 0, 5 times x, and this is a -1, 2, 2 times y, and this is 1, a -3, a -1 times z. And so I should be able to get my matrix from here. So, right? Yeah, because this is my matrix. A -1, 0, 5, a -1, 2, 2, 1, a -3, a -1. If I think about that as adding, then x, y, z. This is exactly equal to this. My -1, -1, 1 gives me my, and times my x, y, z gets me my -1 minus x minus y minus z. So this strategy that the book does is it says, divvy them up into your x's and y's so you can see the columns, and then you can put the coefficients of your variables into that column. And so that here, we did the first step here, and we could rewrite that as a -1, 0, x, 0, 1, y, and sure enough, those are the columns of our matrix that I never wrote down. So, okay. All right, what about the second one? Rotates the plane 90 degrees. So the hardest part here, if you do it this way, the hardest part is figuring out, oh, what's my new x coordinate going to be and what's my new y coordinate going to be in terms of x and y. There is, you're going to read if you haven't already, there is an easier way. We'll talk about it next time. The easier way is you can create these matrices, and all you have to do is think about what happens to the standard matrix, to standard vectors. You just have to think about what happens to 0, 1, and 1, 0. Sorry, 1, 0, and 0, 1. And if you know where those go to, then where they go to become your columns. So we'll talk about that next time. Yes?
Can we maybe do a practice one with numerical values for A, B, C, D?
Uh,
Do it B and C when you would flip it across the y-axis? Or what would be your new matrix?
Yeah, so we're up with time. I'm going to answer this question. If you need to go, I understand. Go ahead and head. So your question is,
If we had a 1, 2, 3, 4 matrix, and we wanted to flip it across the y.
so if you do 1, 2, 3, 4, then you've already picked your transformation. Right? What we're trying to do is figure out what we do put into A, B, C, and D to get the transformation that we want. So here, like x, y, what are we doing? We're rotating it clockwise. So that's going to take this one down to here, and it's going to take this one over to here, right? So 0, 1 goes to 1, 0, and 1, 0 goes to a -1, I'm sorry, 0 and a -1. And so what's happening, it looks like I'm switching, there's some switching going on. My x coordinate becomes my new y coordinate.
Thank you.
You're welcome. Thank you. But then there's a multiple, I have to change this, looks like I have to change the sign of my y or something like that. So, did I get that right?
So if they ask for numerical values in the homework, it should be either 1 or 0 or negative.
Numerical values for what? Like,
I'm not 100% sure. I just glanced at it.
I think it's asking for what is A, B, C, and D to transform X, Y into whatever you're
yeah. Yeah, so usually you're going to be looking for these, for these values here. So I'll try to hit it in the video, like make after class.
Cool. Thank you.
You're welcome.